This is YPIR, High-Throughput Single Server PIR with silent preprocessing. I'm Samir, and this is joint work with David Wu. So I can speed through this because this is the last PIR talk. So yeah, we're doing single server PIR. The client wishes to retrieve an item from a database that the server holds, and the server's not supposed to learn which item the client retrieves. There's a lot of applications to PIR. That's why we have a whole session for it. It's a component of a lot of other privacy-preserving protocols, which I list on the slide. I want to talk about a state-of-the-art scheme called Simple-PIR, which was presented last year at USENIX by Hensinger et al., and talk about its costs. So when we're analyzing a PIR system, we are looking at the size of the query and the response. That's the communication cost. And then we measure the server's computational cost. We measure it as throughput, which is like the rate at which the server can process the database, since the server needs to process the entire database to answer a single query. So just for reference, for like an 8 gigabyte database, these are the costs for Simple-PIR, which is pretty cool. The costs are actually quite low, I think. The query and response sizes are in kilobytes, and the throughput is in gigabytes per second for a single CPU core, which is exciting. But unfortunately, Simple-PIR has this one drawback, which is that there's this offline phase. So you need to download this hint about the database, which we'll talk about in a sec. But that hint is quite large. So it's like megabytes. It's at least 16 megabytes using the schemes that are presented in the Simple-PIR work. And so the motivating research question for this work is just, can we get rid of this offline phase? Can we return to like the naive PIR model where there's no pre-processing, there's no offline communication, and yeah. So just an outline of the talk. I'm going to just quickly go over Simple-PIR and Double-PIR. I'm going to talk about two works that attempt to remove hints and succeed, but make responses much larger in the process. And then I'm going to talk about our work where I will just give you like a preview of our results. We kind of answer the research question in the affirmative, like we're able to get rid of the offline phase and maintain similar costs to Double-PIR. And when retrieving larger items, we make an improvement in the response size over hintless PIR. So starting with Simple-PIR, again, we've seen these slides, so I will also go quickly. So in Simple-PIR, basically, the server is computing a homomorphic matrix vector product between like an indicator vector sent by the client, encrypted under some additive homomorphic encryption scheme, and a database that's like just a square plain text matrix. And so the response and the query are both read-n in size. And they also present in that same work a kind of related scheme called Double-PIR, where you just recurse once on the result. And so the key part of the key observation of the work is just that most of the query can be fixed and pseudo-random for all the clients. And so 99.9% of the query can just be pre-computed, and similarly, the result, that same portion of the result, the corresponding one, can be pre-computed, and we call that the hint. And this is the thing that clients are going to download offline. Now, you can see at this moment that the hint depends on the contents of the database because of the matrix multiplication. So this means that like when the database changes, clients need to re-download the hint. And concretely, they need to re-download the portion of the hint that corresponds to the number of rows in the database that changed. So this is, I just want to emphasize this, that's pretty bad for any database that updates frequently, right? So every client needs to download on every database update a new portion of the hint. So this is like more motivation for our research goal, right? Like, let's get rid of the hint. So a couple folks did try to get rid of the hint, and I'll talk about how they did that. So let's look at the decryption at the end of Simple-PIR. So at the end, the client computes something like this. Basically, they've got their offline hint that they downloaded ahead of time. They've got the online response. They can combine them and get the result that they want. But since we're trying to get rid of the hint, if we focus on the hint here, the observation that these works make is that the hint, the first thing the client does with the hint is just multiply it by its secret key, by its LWE secret key, right? It doesn't do anything with the hint after this. It's just the only value it really needs to obtain from the hint for the rest of decryption is just the product of the hint, the inner product of the hint and the LWE secret key. So the other work basically just says like, okay, can we obtain that inner product without just downloading the whole hint and then computing it locally on the client? And so that's what these two works, Hintless PIR and Tiptoe, by Hensinger et al. And Lee et al. Do. So what they do, the way that they obtain this inner product between the LWE secret key and the hint is they basically do this like double wrapping. So they choose an outer homomorphic encryption scheme based on ring LWE that they evaluate the inner product between the LWE secret key and the offline hint under. So what happens is like, at the end, you get an encryption of the value you desired, the hint times the LWE secret key, and this is much, much smaller. So because we're using a compact scheme here, and D is like 1024, the hint is going from 16 megabytes to 16 kilobytes, and now it's so small we can just send it in the response. So now there's no hint, we just send this packed hint in every response to every PIR query. The downside of this approach is basically that because you are using a second outer homomorphic encryption scheme, the plain text space of the outer scheme needs to be able to hold the ciphertext space of the inner scheme. So the LWE scheme has some ciphertext modulus, and the ring LWE scheme needs to have a plain text modulus that fits that. And that double wrapping increases the response size. That's where we're getting that 10x kind of blow up from, is we're double wrapping. So now we can talk about our work. So roughly our work tries to do the same thing. We try to take a bunch of LWE ciphertexts and go to a bunch of ring ciphertexts because they're smaller. But instead of like prior work kind of homomorphically computing LWE decryption and doing the double wrapping, which we talked about makes things bigger, we try to go directly using an algebraic transform. So the way this works is instead of re-embedding LWE inside ring LWE, there's actually a direct way to like view an LWE ciphertext as a kind of like corrupted or like almost like temporarily embarrassed ring LWE ciphertext. So you can, this is prior work. There's a good work by Chen et al. that shows how to do this. But basically you can, instead of doing like this bootstrapping-like approach that the prior work takes, you can instead just do log D key switches and get to a ring ciphertext that's as packed. And so this is like a great way to shrink the size. It makes the final response much smaller because we're not doing double wrapping. There's a drawback, which is like you need to perform this computation in the online response phase. So this needs to be fast. Like you need to be able to perform this key switching quickly. And luckily, we also show in the work that you can pre-compute a lot of this key switching. You can't pre-compute all of it, but you can do most of the work involved in doing this packing ahead of time. And so we show how to do that. So that makes this viable. And so we take this approach and I'll show you a little bit of the concrete results. Before I do that, just some other things. I don't have time to get into them, but these are other highlights from the paper. We show that when you retrieve items, you should use double PIR probably instead of simple PIR as the base scheme. We show how to batch queries from across clients, and we get like a system Z kind of improvement by taking advantage of memory bandwidth. We show how to pre-process simple PIR hints faster using ring LWE, and we have a nice application to certificate transparency that we explain in the paper. So see the paper for more details on that stuff. So just about our performance. Here you can see like we are similar to double PIR on download and throughput for retrieving small items from an 8 gig database, and we just have no offline costs, which I think is exciting. So we can kind of answer our research question in the affirmative. I would say the query size is a bit bigger. So we are 1.5 megabytes, double PIR is 1 megabyte here. So it's not perfect, but I would say we're mostly yes. Mostly yes, we're able to get rid of hints. And that's exciting. And just comparing to hintless PIR, the response size being smaller does yield like real benefits here. In our application to certificate transparency, the response size being smaller lowers like costs as computed using AWS costs. And for large item retrieval, this is a better comparison directly to hintless PIR because hintless PIR was designed to work on large items. And here the advantage is very clearly just the response size is much smaller. And we maintain the same level of throughput and query size. And we have no hints. I think also speed of light, like from here, like versus simple PIR, how much are we slowing down? You can see the throughput is significantly lower and the queries are significantly larger. So there's more work to do here on getting back to closer to simple PIR. And yeah, the application we show in the paper is about checking whether passwords have been breached. Yeah, so takeaways from the talk. I want to say, I think offline costs matter. I think in the real world, these offline downloads are really hard to get working in practice. We think if you're retrieving small items, use YPIR. You can get rid of offline communication for free. For large items, we still have a ways to go, but YPIR is an improvement over hintless PIR for response size. In general, the broad lesson is maybe when you're doing something like bootstrapping, maybe see if there's like an algebraic solution. You can get better efficiency that way. And yeah, the paper and code are up. We did the artifact evaluation. And yeah, open questions. I want to get smaller queries. That's the last thing. And we should explore getting rid of offline communication, i.e. silent preprocessing for some other applications. So thanks.